Hello and welcome to today's video. In this video, we're going to talk about continuous extension. Now, in some cases, we'll have to deal with a function that is not defined at a certain point or at several points, but that gap might be easily overcome. So sometimes a function is more or less undefined for technical reasons, but there is a continuous function that is mostly the same as the original function, with the exception that it has a well-defined value at the definition gap of the original function. Such a function is called a continuous extension, and we'll define that notion properly in this video. So this is called continuous extension. And to clarify what I mean, we'll start with an example. So let's say you have a function f defined on R with the exception of the origin and a codomain of R. And the function is defined as f of x equals x squared divided by x. And of course, formally, the denominator may not be 0. That's why we have this gap here at 0. So formally, f is not defined at x equals 0. But of course, as long as x is not 0, we can easily simplify that function term. So on the other hand, for x not equal to 0, we have f of x is equal to x squared over x, and we can easily cancel out x. So what remains is this here, x. Thus, we can easily determine the limit of f of x as x tends to 0, and that is 0. So while the function is not defined at 0, it has a well-defined limit. And that means we could easily extend the function f to cover that gap, such that the extension does not have that gap anymore. And that's the idea of continuous extension. We could extend f to R, so that R is the domain of the function, such that the extension, we'd call that f bar, is then a function from R to R, is continuous on R, by setting f bar of x equal to x. And then that function would be the same as the original function f on all points except x equals 0. And for x equals 0, it would be continuous. So this is the idea of a continuous extension. Let's just define that notion properly. So here's a definition. As usual, let I subset of R be an interval. Let x star be some point in I. And let f be a function on I with the exception of x star. And a codomain of R. So that is a function such that the limit of f of x as x tends to x star exists. And the existence of that limit basically means there is no good reason for f not to be defined at x star. And thus we can extend that. So the function f bar defined on the interval I with no exception anymore, codomain R, defined as either f of x for x in I with the exception of x star. So function is identical to f of x for all the points that are in the domain of f of x. And for the only point not in the domain, for x star, we just define the function value as the corresponding limit of f of x as x tends to x star. So this function is then called the continuous extension of f to x star. And of course, if x star happens to be a boundary point of the interval, then you would replace the limit by the corresponding one-sided limit. So just as a side note, if x star is a boundary point of I, the appropriate one-sided limit must be used. And by appropriate, I mean the one-sided limit that is actually well defined. Okay, we've seen one example already. Let's have a look at a couple of other examples for continuous extensions. The first one, let's say we have the function f defined on the interval from -1 to infinity with the exception of 0. And the definition of that function is f of x is the square root of x plus 1 minus 1 over x. So this function is obviously not defined at 0 because we would divide by 0 here. And it's only defined as long as this argument is non-negative. That's why this minus 1 here is the left boundary of the interval. Now the question is, does a function have a continuous extension? So we need to ask, is there a limit of f at the point 0? So let's have a look at that. Want to determine the limit. Now this might look familiar if you have watched some other videos already, but just for the sake of completeness, let me give a brief summary of how that limit can be computed. So we want the limit as x approaches 0 of the function square root of x plus 1 minus 1 divided by x. What we do to compute that limit is we multiply the function by an appropriate term to get rid of that square root here. And that appropriate term is, of course, square root of x plus 1 plus 1 instead of minus 1, so that we can make use of the binomial theorem. And we multiply with the same argument here in the denominator, so that in effect we multiply the whole expression by 1. Right? So this here, this cancels out, and we're back to the original function. Now, if we do that, what we get here is In the numerator, we apply the binomial theorem. We get this term squared minus this term squared. So we get x plus 1 minus 1, and that's just x. And in the denominator, we get x and square root of x plus 1 plus 1. So we don't change anything here. And now the x cancels out. And all that's left is a limit of x to 0, 1 over square root of x plus 1 plus 1. And now this term here, this goes to 1. So what we have is in effect 1 over 2. That means this limit does exist. So if we just set the function value to that limit, then we get an extension of f that is continuous at 0. So what that means is that f can be continuously extended to x star equals 0 by setting f bar of x, the extension, to f of x for x in -1 to infinity with the exception of 0, and 1 over 2 for x equals 0. And then we have extended f appropriately. Part B, final example here. That's a counter example now, showing that not every function can be continuously extended. So if we have a look at the function defined again on R, with the exception of 0, codomain is R again. Another function is f of x equals 1 over x. Now what we get here is, if we take the limit of f of x from above, so the interesting point is of course 0, so we want to see if the function has a limit at 0. And if we approach 0 from above, that means we take in the limit of 1 over x. X approaches 0 from above. So from above in particular means that x is greater or equal to 0. And that means this expression here is positive. As the x becomes smaller and smaller, this expression becomes larger and larger. So in particular, it can become arbitrarily large. And that means this whole term will tend to infinity. And as it is always positive, it will tend to plus infinity. So the limit cannot exist. We already know that, but just for the sake of completeness, let's also have a look at the limit as x approaches 0 from below. Now what we get here is, now in this case, x is less or equal to 0 because it is approaching 0 from below. And that means this expression here is always negative. So again, in absolute values, this expression can become arbitrarily large, but it is negative. So that means the limit here is minus infinity. So altogether, we can conclude immediately that no continuous extension to x equals 0 is possible for this function. And just to reiterate, we would have known that here already, because infinity is not a finite limit. We need a finite limit for a continuous extension. We cannot define a function value of infinity. Okay, so this would have been sufficient. That's just for the sake of completeness here. So this concludes our brief treatment of continuous extensions. And as usual, I hope I'll see you in the upcoming videos.